Hello. In this video, I will show you the main simulation settings that you can use in Interface Equilibrator. As illustrative example, I will consider a droplet wetting a spherical solid surface. So, to set up this configuration, I first add a fluid mesh for the droplet. Then, I add a new mesh for the spherical solid surface. So, I select the built-in spherical mesh, selecting its high-resolution version. And then I load it. Now that the spherical solid surface is loaded, I translate it opportunely so that the droplet can be placed above it. Finally, I select the solid sphere as the constraint for the boundary of the droplet's mesh. The initial configuration for the simulation is now ready. Before starting the equilibration, I save the current configuration for later convenience. If I now click Start Equilibration, the droplet's equilibrium shape is computed using the default settings in Interface Equilibrator. Let's now reload the initial configuration we saved before, so I can show you how you can easily adjust these settings. Firstly, we launch the Equilibration Settings form, and then we select the Equilibration tab. In this tab, you can find the most important equilibration settings. This trackbar regulates the refinement of the fluid mesh during the equilibration. The higher value you select, the more refined the fluid mesh will be with respect to its curvature after the equilibration. We have now selected the lowest degree of refinement. Therefore, after launching the equilibration, the mesh that we obtained for the droplet's equilibrium shape is much less refined than the mesh we obtained before. If we now select the slightly higher degree of refinement, and then start the equilibration on the current droplet's mesh, you can see that the newly obtained mesh is now refined a bit more than before. And by selecting even higher degrees of refinement, we can obtain more refined meshes from the equilibration. If I now select the highest degree of refinement, you will see that the mesh refinement after the equilibration does not change anymore. The reason for this is due to this setting here, because it is selected to not refine fluid meshes with more than 500 vertexes. So, I increase this value to 5,000. As you can check by right-clicking on the droplet node in the tree diagram and then selecting number of facets. This droplet's mesh has about 2,500 facets. So, its refinement should now be allowed during the equilibration. As a matter of fact, after launching another equilibration, the droplet's mesh was now further refined. You can also disable the refinement of the fluid mesh altogether. And you can disable also the other methods that polish the fluid mesh during the equilibration by deselecting this option. Then, during the equilibration, the fluid mesh triangulation is not edited at all. If you then reselect this option, the mesh will again be refined and polished during the equilibration. And by deselecting it again, you prevent again that the mesh triangulation is edited during the equilibration. For example, if I now change the Young's contact angle, and then launch another equilibration, the droplet's equilibrium shape changes, but its triangulation remains fixed. If I reactivate this option, then, when launching the equilibration, the droplet's mesh will again be refined and polished. I will now show you another very useful equilibration setting. If you select this option, then, during the equilibration, the volume of the fluid below the fluid interface will be varied by the selected value. For example, I select to increase the fluid volume by 1 cubic micron. The fluid below the fluid interface is the fluid inside the droplet. So, by launching the equilibration, we increase the droplet's initial volume by 1 cubic micron. Let's try a 5 times larger volume increment for the droplet. So, this time, after launching the equilibration, the obtained droplet's equilibrium shape will have a volume that is 5 cubic micron larger than the droplet's initial mesh. Let's try an even larger volume variation. For example, 30 cubic microns. As long as the option to vary the fluid volume is selected, then the volume variation will be enforced whenever launching a new equilibration. So, if I now launch a new equilibration, the current droplet will be enlarged by another 30 cubic microns. If you want to assign a precise total volume to a droplet wetting a curved substrate, then this option to modify the fluid volume becomes quite useful. For example, consider the configuration that we saved before. The droplet's exact initial volume is not easy to determine, because it consists in the volume of this polyhedron, minus the volume of the sphere that overlaps with it. So, to assign a precise total volume to the droplet, we remove this initial droplet mesh, and we introduce a droplet initial mesh with a much smaller volume, say 0.001 cubic micron. This smaller droplet was now introduced. Let's zoom in to see it more closely. This time, when we set the solid sphere as the constraint for the droplet's boundary, we obtain an initial shape for the droplet that has a volume of roughly 0.001 cubic microns. So, if we wanted to simulate a droplet with a volume of exactly, say, 1 cubic micron, we just need to enable the option to increase the droplet volume and set the volume variation to 0.999 cubic microns. Then, after launching the equilibration, the obtained droplet will have, with a very good approximation, a volume of exactly 1 cubic micron. Thank you for having followed this video. For more information and for other tutorial videos about Interface Equilibrator, please visit our website.